Hello all, welcome to this lab class. Here we will look at one more physical deposition technique. In the last class we have seen E-beam evaporation. In this class we will see sputtering. What does sputtering do? If you recall our theory class, sputtering is a technique which is a mechanical way of depositing the material. That means you are dislodging the atoms from the source and depositing onto the substrate. Here you are not doing the heating. So, there is no flow of current through the source, right. Here we are using argon to create the plasma, and the advantage of sputtering you already know that over thermal and E-beam evaporation, the sputtering has advantage that it has a better step coverage. So, let us see how sputtering system works, how it looks like. We will show it to you again the entire process. It will be close to half an hour time, because again we will see that how the system looks like and how can you create a vacuum, and actually you can see the system from within. Lab that I want to show it to you, where you can see the substrate holder. Here you will see the plate instead of having a source, and this plate is on the magnets. So, we call it as a magnetron sputtering. Also in the sputtering system that you will see, there are two kind of ways we can sputter. One is called direct sputtering or DC sputtering. DC is not called direct sputtering, it is a DC sputtering, and its second one is a RF sputtering. Now the use of this magnet is what we call as a magnetron, right, is to improve the rate of deposition. If you use magnetron along with the, so if there is a magnetic field along with the electric field, the rate of deposition of the material would improve. That is the reason of having magnetron sputtering. We have DC magnetron sputtering and RF magnetron sputtering. You will see in the lab component. I will see you at the end of the lab class.
Hello everyone, welcome back to another lab session of this course. Today we will be talking about another PVD technique, which is sputtering. In the previous session we saw one of the PVD techniques which is thermal and E-beam evaporation. Now if we already have a PVD technique, why do we need another tool in the same lab? So the difference lies in your requirements. First thing, there are certain trade-offs between both the tools. So for example, the E-beam, what essentially you do is you are melting off a material, and after melting you are taking the vapors actually naturally they flow and stick to the surface. So what happens is you have to melt the material completely. That goes well with metals like aluminium and gold, which have comparatively lower melting points. Also, when you are melting a material, you need to contain it in some crucible, and that crucible should not melt off along with it. So when you are talking about materials like aluminium, gold and titanium, you can place them in a boat of tungsten, which has a very high melting point, and that is the reason it is used as a filament in certain cases. So, but what if you want to deposit tungsten, a material like tungsten which has a high melting point? It is practically impossible. So in that case we move to sputtering. I'll explain the process in a few minutes. Another reason that we might want to shift to sputtering is the stoichiometric ratio. Suppose if you are not depositing a pure metal, you need an alloy. Let's say it has a 30-70 composition of A and B. When you are melting it off, like using E-beam or resistive heating, it might happen that component A might have a different melting point than component B. So although you have a source which has a 30-70 composition, the rate of melting will vary because depending on the melting point, and on your sample what you will have, the thin film that you will have might not have a 30-70 composition. It might have something like 10-90 or 50-50. It's not, you don't know. So in that case also we will move to sputtering. The third trade-off is when you are depositing using a thermal technique, the final layer, the film that you get is quite smooth. It might sound good, but in certain cases you might not want a smooth layer. Maybe your device or the device or your requirement demands that you should have some roughness, maybe in nanometers. In that case also sputtering will be the go-to choice, because the final layer that you have after sputtering is not smooth. So let's talk about what exactly happens in sputtering. Mainly we use the main thing that we have in sputtering is plasma. So what happens is usually we are using an inert gas like argon, which won't react with your sample or your source. That's why we use argon. So what happens is when you have you pump in argon gas between a very strong electric field, the bottom will be negatively charged and the top will be positively charged. So what happens is due to a very strong electric field, the argon splits into an positive argon ion and an electron. Now what happens is this positively charged argon ion will rush towards the negatively charged electrode, and meanwhile, while traveling towards this electrode, it will encounter other argon ions and it will collide. Due to this physical collision, some more argon atoms might split into electrons and argon ions. This sort of continues like a chain reaction, and ultimately you have a steady state where you have sustained a plasma. This argon ions, the bunch of argon ions moving towards this electrode will create what is called as a plasma, and the indication is usually it will be some purplish glow that you will see near the electrode. Now that we know how to create an argon plasma, what is the use of it? So what happens is, since I mentioned earlier that the bottom plate will be negatively charged, and that is where our sample will be. So when the argon ions are moving towards this negatively charged, not sample, but your source, the desired material that you want to coat, will be placed on the negative electrode. So when the argon ions are rushing towards this source material, they will directly hit and impinge. They will impinge on the source material and dislodge some molecules of it. When you do this multiple times for a long time, when such a thing happens, this dislodged particles will, due to the kinetic energy, will move to upwards, and on the bottom positive electrode you will be having your sample where do you actually want the coating to happen. So this is the basic principle. You pump in argon gas, apply a very strong electric field, create a sustained plasma, and this plasma will dislodge the particles from your source, and these dislodged molecules will go and stick to your substrate. So now next thing we'll be seeing the actual demonstration of this tool. For now I have a source material, a sample source material, which is called actually a target, which we'll be using in this tool. So this is a 3-inch copper target, and obviously we'll be using when we want to when we need a thin film of copper. While we are operating the tool, I'll show you this closely, and you'll appreciate that the part where the actual plasma hits is a little shiny compared to the peripherals. Now that we know the working principle of the sputtering tool, let's operate it and have a small demonstration. So firstly, I'll switch on the main supply. Before that, this is the sputtering tool, as you can see, ATS 500. which is manufactured by an Indian manufacturer, HHV. So we'll start the main supply and carry out the deposition. Now that I have turned on the main supply and also the supply to the chiller unit, for which you can see there are one inlet and outlet which is connected to the water jacket around this chamber. This is the chamber where the vacuum will be created and a plasma will be created later on once the vacuum has reached. So like it's obvious that when such a reaction is happening inside, when the plasma is created, it is bound that there will be some increase in the temperature. Also, there is a heater unit attached to this in case you want to do the sputtering at higher temperatures. So, to avoid any mishaps, like a person, the user might accidentally touch this chamber and get injured because of the heat. We have this water jacket which constantly cools down the chamber from the outside. So let's switch on the tool and see what options do we have. So now we have turned on the tool, and this is the screen you will see when it has completely booted up. So you see this is the main menu, and you have certain options, of which normally you would be using only 3 or 4. So the important ones are manual, system control, source control, and there is a system view if you want to see. So let's see what we have in system control. As you can see, this is the system control, and here we have certain values on the screen: the backing pressure and the roughing pressure. Right now, the pressure is a little high, as in the vacuum is really bad. It is 10 to the power 0, and the system is in standby. So first, to start the process, what we will have to do is take the system from this pressure to 10 to the power minus 6. That is a very high vacuum. But before that, we'll have to vent the chamber, take out the substrate holder, mount a sample, and then we'll start the process. So right now you see only 2 options are highlighted: start and vent. So what start will do is it will start the it will start the pumps. I'll come to that in a minute of what kind of pumps we have. Then we have this option vent. Vent will just let the atmospheric air into the chamber, and so that we can open the door and take a look at the chamber. Other non-highlighted options are stop, process, seal, and cycle, which we'll see in a minute. Then we have some system view and source control, which we'll see in a minute. So for now, let's vent the chamber and take out the substrate holder. I'll click on vent, and now you might hear a hissing sound. Yeah, it means that the atmospheric air is entering the chamber, and it is about to reach the atmospheric pressure. So now the chamber is completely vented. What I'll do, and you can see that the pressure is 10 to the power plus 3, which is the atmospheric pressure. Now, once this is completely done, I'll seal this chamber and open the chamber door. Before that, I'll start the pumps so that they are in running conditions, and we'll save some time. And you might be able to hear a sound of the roughing pump. I'll show you it in a minute what all pumps we have. So now, since the chamber is completely vented, we'll open the door and see what's inside. So now you can see what we have inside this chamber. These are the electrode setups. The first one is for RF sputtering. The second one on the right is for DC sputtering. Here we have the shutters that ensure that you have a sharp control over the thickness. So when you want the deposition to happen, you remove the shutter, and when you don't want the deposition, the shutter will cover this target. In this electrode setup, there is an adjustment for the height as well as the angle, and here inside this we have the target. For example, I had shown you a copper target a few minutes before, that is placed inside this, and there is this shutter which covers the target. Then we have here the substrate holder, which keeps on rotating during the deposition to ensure uniformity. Above that, we have two heaters. In case you want the sputtering to happen at a higher temperature, we will switch on the heaters. So that's it, and we can now start with the process. So before starting the process, the most important thing is to fix the sample on this substrate holder. So I'll take out the substrate holder or the chuck carefully, with making sure that I do not hit any or other components. So this is a 10-inch chuck which rotates during the deposition, and we'll be fixing a glass slide on this chuck, and with the help of a Kapton tape, and we'll be depositing tungsten. So as you can see, I have fixed a glass slide on this chuck. I'll be placing it inside the chamber and starting the vacuuming process, which is also known as the cycling process. Again, we have to be really careful that while placing this substrate holder, we do not touch our samples with the hand, or hit any of the components with this substrate holder. It's done. We'll close the door. Now that I've placed my sample attached on a sample holder inside the chamber, so before starting the process, the crucial step, most important step, is to reach the desired vacuum level, a very high vacuum of the order of 10 to the power minus 6 millibars. So after placing the samples in the chamber, I'll start the evacuation process, or the cycling process as we call it in this tool. So I'll click on cycle and allow the backing valve to close. So what will happen initially is the roughing pump will come into action and reduce the pressure from the atmospheric pressure, that is 10 to the power plus 3 millibars, to a high vacuum of 10 to the power minus 3 millibars. Next, once that is done, the next action would be of the turbomolecular pump, working in series with the rotary or the roughing pump, to reach a very high vacuum of the order of 10 to the power minus 6 millibars. So we'll wait for now till the pressure reaches 10 to the power minus 6 millibars, and then we can start with our process. While we are waiting for the vacuum to reach the desired level, let's have a look at the various control this machine offers. So at the bottom you can see this is the DC power source. There is the mains for the DC power source, and various controls for setting and reading voltage, current, and power. The next thing we have is the RF power source. This display shows the various parameters that we have while using the RF power source. Next is the DTM, the digital thickness monitor, which is coupled to the quartz crystal oscillator, which we have seen inside the chamber, and it works on the principle of frequency shift when more and more mass is loaded on the crystal. Here we can see the temperature monitor. So it is right now set to 300, but since the heater is not on, as we are not doing the process, the heater is right now off, and the chamber is right now at 27 degrees Celsius. The next we can see there is the power and reset button and the emergency off button. The main control that we have is through this HMI, or the display panel. So right now you can see it is showing the process which is going now is fine pumping, and we have certain options, and the pressure is indicated. Let's have a closer look to what other options we have. So this is the display panel, as we said, and you can see the pressures here. Right now the chamber pressure is 8 into 10 to the power minus 6 millibars, and while the fine pumping is going on, the options that you have right now is seal, process and vent. Vent will evacuate the vent will let the atmospheric pressure rush in, and the chamber will come back to atmospheric pressure. So next is the seal, which will seal the pumps from the chamber when you are opening it. And this is the process which we will be going into this option once we reach the desired pressure. So meanwhile, let's have a look at the main menu. The main menu has various options, of which what is important to us is the alarms, the system view, and this system and source control. So let's go to the system view and see a schematic of this tool. As you can see here, some pressure sensors are displaying their values. This is the chamber, which has two magnetrons, two magnetron. SH1 and SH2 are the shutters. This is for RF, and this is for DC. We have various pressure sensors and valves connected to it. The most important thing that I wanted to show you is these two pumps. You can see this is the roughing pump, or the rotary pump, you might say, and this is the turbomolecular pump. So what happens is, when we start the cycling process or the evacuation process, these two valves will be closed, and the entire pressure will be reduced from atmospheric pressure, that is 10 to the power 3 millibars, to 10 to the power minus 3 millibars through this line using the roughing pump. Once you reach a high vacuum such as 10 to the power minus 3 millibars, these two valves will open, and the sequence would be this chamber will be connected to the turbomolecular pump, and then it goes to the roughing pump. So what happens is, this turbomolecular pump will take the pressure from 10 to the power minus 3 to a very high vacuum, that is 10 to the power minus 6, and so these two pumps will act and work in a cascading method. Now let's go back to the system control. Now we'll go to the source control and see what all options we have. So here you can see this is the menu for RF power. If you want to use RF sputtering, you will enable the RF power and then set the whatever parameters you want, the power, and you can see the reflected and forward power here. And here we have options for inletting two gases. One is argon, and another is some other auxiliary gas you want. We will enable which mass flow controller or MFC we want, and monitor set the flow rate and monitor them here. Next we have the DC power. We'll enable it, and here we have the shutters for two magnetrons. On the left we have RF, on the right we have magnetron 2, that is the DC. And here is the option for DTM. If we enable it, you can see it starts displaying values. Next you can see there is an accessory control where we have this rotary, that is the rotating chuck or the sample holder, and we have an option to enable the heater. Like I said, in that ETM it was showing that the current temperature is 27, and we can set and it was set to 300. We can choose any value from between the room temperature to a maximum of 300 and enable the heater. So it will take some time, and finally you will reach the desired processing temperature. Now let's go back to this source control, and here we have the system control. Now you can see the pressure has reached somewhat around 7.7 into 10 to the power minus 6 millibars. So we'll wait for some more time, and then we can start the process. So the desired pressure has been reached, and we can now start with the deposition process. So of all this, right now we are in this system control, and we'll be choosing this process option. Now it goes to throttle pumping and the process sequence has been enabled. Now we can go to the source control, and now like we said, we have certain options like RF power, DC power, and the mass flow controller, gas valves. So since we are depositing tungsten today, we'll be using DC power. So I'll just enable the DC power. You can see these panels have lit up. Next, I'll be also enabling the gas valve. Next I'll open the valve for argon gas. I'll now enable the mass flow controller for argon, and right now the set values for voltage and current are 0, 0. So the parameters which we have optimized are 600 volts and around 0.5 amperes of current, which will roughly give us a power of around 280 to 300. So I'll slowly increase the voltage. You might notice that the power is not increasing, and we are setting the voltage and reading the power and setting the current. So unless and until as long with the voltage I give some current, there won't be any power. So we are now at 600 volts, and slowly I'll be increasing the current as well. Meanwhile, I'll also enable the gas flow. So I'll be setting this argon MFC to 12 SCCM, but in steps. First I'll keep it at 5. Let it reach 5. And slowly I'll also be increasing the current. Now it has stabilized at 5 SCCM. I'll be increasing it to 12. I'll also be monitoring the plasma through the viewport. So the power was set at 300 volts, 300 watts, I'm sorry, and still the power is not showing. That means there is no plasma right now, and that is why you cannot see any power being delivered. I'll just enable the shutter for a moment to see if there is any plasma strike. Not yet. I'll be increasing the argon flow. So now the plasma is sustaining. As I can see in the viewport, we have a very bright blue plasma, and the parameters that we have right now are 600 volts, around 280 watts at a current of around 0.53 amperes. So now we can start with the deposition process. I'll just enable the DTM, the digital thickness monitor, and reset it by stopping and starting. So now it is reset. I'll be opening the magnetron 2 shutter, which is for the DC sputtering, and noting the time. We'll be depositing for around 10 minutes, and the thickness which we would be having, we'll see. It would be somewhere around 100 nanometers. So we'll wait for 10 minutes, and when the process is complete, we'll have a look at the sample. So it has been around 5 minutes, and apologies, I said it will be around 100 nanometers, but turns out the parameters are such that for 5 minutes it will give a thickness of around 200 nanometers. So now I'll just disable that shutter. So what will happen is the shutter will cover my magnetron. So whatever deposition is happening, it will be on the shutter, and it won't be on my sample. I've disabled it, and I'll also disable the DTM now. Slowly I'll reduce the current. So the sequence was, first we set up the voltage, and then we slowly increase the current. We'll go in a reverse order. We'll first start reducing the current and also the argon flow. So you'll see, as I am reducing the current, the power also reduces. As we know that power is basically the function of voltage and current. So that makes sense. As we are reducing the current, the power will also go down. And we have an extinguished plasma. So now it is 0. I'll also reduce the gas flow first to 5 SCCM, and also start reducing the voltage. Now I'll reduce the gas flow even further, basically make it 0. Once it is stabilized at 0, I'll turn off this mass flow controller and the gas valve. I'll also now disable this DC power source, and now only the vacuuming is going on. So what I'll do, I'll also, I forgot to mention, we also had the rotary drive in motion at 10 RPM. I'll disable the rotation and go to system control. And now you can see the pumping is still going on. So now what I'll do, I'll seal my chamber and put it on cycle for a few minutes. So that whatever residual gases which were we were having, it will be taken out. Now we'll allow it to cycle for a couple of minutes, and then we'll come back and vent our chamber and take out the sample. So now we have allowed the chamber to go for cycle for a couple of minutes. Now next thing would be to take out the sample from the chamber, which is right now in a vacuum evacuated condition. So the next thing would be to vent it out. So I'll just click on vent, and as the venting starts, you might be able to hear a small hissing sound, which indicates that the atmospheric air is entering the chamber. So once the venting is complete, we'll open the chamber, take out the sample holder, and we'll be showing you the deposited sample. Now the venting is complete and the chamber is at atmospheric pressure. So it is safe to open and take out the samples. Now you can see there is a mirror-like finish on the sample that we have, the glass slides which we had initially kept, and this is due to a thin 200 nanometer coating of tungsten. So we'll just take it out and put the chamber back in vacuum conditions, because the more the longer it is kept at atmospheric condition, the more the chamber keeps on degrading. So it is a good practice to always keep it at a evacuated condition.
So, what you have seen in the this particular lab is sputtering, right. Now, sputtering can be a DC sputtering and sputtering can be RF sputtering. We have a system which has both DC sputtering and RF sputtering, which you have seen. Additionally, you can always bring the source to the substrate distance closer without, and also you need to understand that the reason of having vacuum in all this physical vapor deposition is to have a better mean free path, right. Mean free path, as you may know, is a path before which how much the atoms will travel before colliding with another atom. So, how much if the distance is more, less number of collision, the better the deposition. The mean free path can be improved by having a vacuum of high value, for example 10 to the power minus 6, minus 7 and so on, the better the mean free path is. Going back to the sputtering, in sputtering we can do magnetron sputtering and non-magnetron sputtering. So, DC magnetron, RF magnetron, or DC sputtering, RF sputtering. The reason of using this magnetron again is to improve the rate of deposition. So, this is all about the sputtering system, and using sputtering you can, like I said in the theory class as well, that the sputtering will overcome the limitations of thermal evaporation and e-beam evaporation by having a better step coverage. The difficulty with sputtering system is it is a low throughput system, only one wafer at a time you can use it. You may have already seen in the lab class that we have a plate which is having a source, right, or a material that you want to sputter, and you have a substrate holder. Because we have DC and RF both, you can change the angle of the source, so to use each in respective position. Generally you should have the source and substrate right on each other like this. Anyways, so this is all about the sputtering system, and I hope that you have now a little bit better understanding of how sputtering system looks like and how you can operate the system. So, now I will stop this particular lecture, and I hope that you have understood from this lab component as well as previous lab component how the e-beam evaporation and sputtering system looks like, and again you need to follow the lab gowning protocol while entering the clean room. I will see you in the next class with one more lab. Till then, you take care. Bye for now.